All right, so let's look at one of these confidence intervals for the variance. Xenical is used to treat obesity in people with risk factors such as diabetes, high blood pressure, and high cholesterol or triglycerides. Xenical works in the intestines where it blocks some of the fat a person eats from being absorbed. A standard prescription of Xenical is given in 120 milligram capsules. Although the capsule weights can vary somewhat from 120 milligrams and also from each other, keeping the variation small is important for various medical reasons. A sample of 9 Xenical capsules has had the weight shown in the table below. The mean of the data set is 120. The sample standard deviation is 0.19. Assuming that the population is normal, construct a 99% confidence interval for the variance of all Xenical capsule weights. Okay, so we're going to do a confidence interval for population variance here. Okay, so let's take this thing through the whole example. Our procedure is always going to involve a chi-squared when we're doing variance. So let's see. There we are, one variance, chi-squared procedure. Our assumptions. Well, let's notice up here, we can assume the population is normal, so we've got that. Sample size is not greater than 30. Population standard deviation is not known, so we really want this one. Number of positive and negative responses are not greater than 10. We've only got 9 responses here. And although it doesn't say, we can, in most scientific studies, assume that it was a simple random sample. Okay, our unknown parameter here is our population variance. So right there, our point estimate, we're going to use the variance for the sample. So S squared. And in this case, since it gives us the sample standard deviation, we just want to square this to get the sample variance. So 0.19 squared, I'll just put that in my calculator, is 0.0361. Okay, our confidence level is 99%. And alpha, in that case, when we have a 99% confidence interval, remember alpha is 1 minus 0.99, so it's 0.01. If we divide alpha by 2, that's 0.005. And then if we take that 0.005 and subtract it from 1, that's 0.995. All right, now, with these two values in mind, and let's notice that we had 9 pieces of data up here. We're going to use the chart from the tables that are in Blackboard. All right, so you'll need to go to the tables that are in Blackboard to complete these exercises. But I'm going to start with the 0.995 because generally that will be our critical value on the left, even though these are kind of backwards of that. All right, so we have 9 items, so 9 minus 1, or 8 degrees of freedom. On our chart, our table, we want the table that is the critical values of chi-squared distributions. You notice there's our symbol for chi-squared right there. All right, so let's look up degrees of freedom of 8 and 0.995. Okay, so degrees of freedom of 8, 0.995 is 1.344. Go ahead and put that in. Whoops, where am I? So, 1.334. Now, we always want the smallest number on the left and the biggest on the right, so if these turn out to be the opposite of that, we'll switch them. But let's look up 8 degrees of freedom and 0.005 on that same chart we just saw. All right, so 8 degrees of freedom, 0.005 is 21.955. Okay, so 21.995. Margin of error we do not have when we're doing a confidence interval for variance, so we're going to type in does not exist here, DNE. If you don't type something there, it will count it wrong, so put DNE. All right, so our lower bound. All right, so now let's do the calculations for the actual confidence interval here. Here's our formula. We're going to take n minus 1, multiply it times our sample variance, S squared, and then whatever that answer is, we're going to divide it by our chi squared. I'm just going to use an x for chi just to make it easier to type, but that's not really a chi, but we'll say it's a chi. Whatever we get for our chi squared, that's what's going to go on the bottom. Now, we just did the chi squared calculations from the table. So, in other words, if I go back, here's my first chi squared, and here's my second chi squared. Okay, so we're going to take, first, let's do the n minus 1 times s squared. N minus 1, our n is 9 in this case. We have 9 in our sample. So we'll have 9 minus 1, and then we did our s squared right here. It's 0.0361. So we're going to have, whoops, whatever. All right. We're going to have 9 minus 1 times 0.0631. And I think I've got that right. Let me make sure. 0361, yeah. Okay. All right. So really, that part right there is 8 times 0.030631. And I'll put that into the calculator. And I get 0.5048. Now, there's a reason why I calculated this separately, because we are going to do two calculations. We're going to divide this number by the two chi-squared values that we had. So let's go back here for a minute. Our first chi-squared value was 1.334. Now, it may seem weird. We're dividing by the smaller number, though, so this is going to end up being the right side of our confidence interval rather than the left side. And we'll see that, of course, dividing by a smaller number leads to a bigger answer, whereas dividing by a bigger number leads to a smaller answer. So this gives me, and I'm not sure how many decimal places that it asks us to go to, so I'm going to write out about 5, and then we'll round it off here in a minute. And then let's do the other calculation, 0.5048 divided by the other chi-squared value. So I need to go back here for a second. My other chi-squared value was 21.995. So 21.995. Let's put that in the calculator. And we'll end up getting 0.02295. Now let's notice that this is the smaller of the two values. So when we put it in, the one that's smaller needs to go first. And I'm betting it's 3 decimal places, but let's look back here real quick. All right, yes, answer to 3 decimal places. So I want to put 0.023 for the first one, the lower bound. 0.023. And then I want to put 0.378 for the upper bound. 0.378. And my confidence interval is those same numbers. And then let's do our interpretation. This was a 99% confidence interval, so we are 99% confident that the true population variance is between 0.023 and 0.378. Based on the confidence interval, we want to know, is it reasonable to believe that the population variance is greater than 0.06? Now let's notice that 0.06 is in there, but there are still values that are less than 0.06 that are in that. So we want to say, well, no, we can't assume that the variance is greater than 0.06 because it could be 0.03, for example. All right, so we want to say no because a part of this interval is below 0.06. So part of the entire interval is below 0.06. There are numbers like 0.03 that are below 0.06, and that could be the actual population variance. And all of these are essentially the same. They are long, but you've only got 4 of them.